Assalamualaikum and good morning everyone. In this video, we're gonna learn about the force convection that happen externally, which is outside the various geometries. First, we look at the flow that is parallel to flat plate, and then flow that pass cylinder with axis perpendicular. Next, we look at the flow past single sphere, and finally, the flow past banks of tubes or cylinders. In general, heat transfer that is occurring between the fluid and the immersed bodies of solid spheres, tubes, and plates only. The heat flux is dependent on the geometry of the body, the position on the body, whether the body is on the front, the side, back, the flow rate, and also the fluid properties. Therefore, the average heat transfer coefficient on the immersed body is given by this Nusselt correlation, which is equal to C Reynolds number raised to m and Prandtl number raised to 1/3. Here, the C and m are constant that is obtained from table 4.61. Table 461 is shown here. So the table is actually for various conditions. You have to first identify the Reynolds number for that flow regime, and then finally, based on the Reynolds number, we will get the respective m and c constants. The fluid properties are evaluated at the film temperature. So the definition for the film temperature is as shown here, where the Tw is the surface of the wall temperature plus the average bulk fluid temperature divided by 2. So let's look at the first one. The flow parallel to flat plate. So we consider this parallel flow of a fluid. So the blue arrow here is the cold fluid that is flowing over a plate. Okay, this plate has a length of L meter in the flow direction. So here, okay, this flow is transformed to this diagram. Okay, so where I want to show you that when there is a parallel flow over flat plates, the flow could either be in laminar region or turbulent region, depending on how far that the x coordinate is measured along the plate surface here. Okay, so this is x equal to 0. So the laminar velocity will happen up to at a distance x critical from this leading edge, where the Reynolds number will reach its critical value for transition. Okay, so this is the critical value for Reynolds number for the flow to transition into turbulent. So the transition from laminar to turbulent is depending on the surface geometry, the surface roughness, upstream velocity, surface temperature, and also the type of fluid. Okay, so all of these factors that will influence the transition from laminar to turbulent flow is best characterized by this Reynolds number. The Reynolds number is measured at a distance at x coordinate from x equal to 0, which is the leading edge of a flat plate. So the Reynolds number with this subscript of L means that the Reynolds number is at the far end of the plate. Okay, so from here we can also observe that the Reynolds number varies for a plate along the flow. So when it reach the L meter here, so that is why the Reynolds number has the subscription L over here. So Reynolds number can be calculated using this formula, where rho multiplied with the fluid velocity, length of the plate, divided by the viscosity at the end. Okay, so the Reynolds number L is happen at the end of this flat plate. So now let's look at what types or what are the correlations that we can use for the laminar region. So for the laminar region, the Nusselt correlation that will be used is this one. Okay, this only applies for when the Reynolds number is less than 3 times 10 to the power of 5 and Prandtl number is greater than 0.7. Meanwhile, for the tubular region, the Nusselt correlation is as shown here. Okay, the tubular region Nusselt correlation is applied when the Reynolds number is greater than 3 times 10 to the power of 5 and Prandtl number is greater than 0.7. Now let's look at this example 2. A smooth, flat, thin fin of copper extending out from a tube. Okay, this is the dimension 51 millimeter width and 51 millimeter square. Its temperature is approximately uniform at 82.2 degrees Celsius. So this is the surface or wall temperature. Cooling air at 15.6. So this is the cold fluid, which is the cold air. The temperature is 15.6 degrees Celsius, P1 absolute atm, and then the velocity of the cold fluid is 12.2 meter per second. Part A, for laminar flow, calculate the heat transfer coefficient. Okay, so for laminar flow we will use this equation, okay, to find our H. But first we have to evaluate the fluid properties. Okay, so for the fluid properties, you have to determine the fluid properties at the film temperature. So the film temperature is Tw plus Tb divided by 2. So it is around 49 degrees Celsius. So then you can go through to appendix A3, okay, and then look at Tf at 49 degrees Celsius. Then you have to determine the mu b, the Prandtl number, the thermal conductivity, and also the rho of the fluid. Okay, so first we determine the film temperature. Next we determine the fluid properties at film temperature. Okay, next steps, we are going to calculate the Reynolds number at L, okay, at the length of the flat plate. So Reynolds number is equal to L multiply with velocity rho divided by mu. Okay, so all this rho and mu you can get from the second step. Okay, so we just plug in all the values and then we will obtain the Reynolds number as 3.49 times 10 to the power of 4. So obviously this is less than the 3 times 10 to the power of 5. So the flow is laminar. So for laminar, next step, okay, find the corresponding Nusselt correlation, whether it is laminar or turbulent depending on the Reynolds number. So since our Reynolds number is in laminar region, so we will use this Nusselt correlation to find our H. Okay, and then you plug in the length of the plate, K, Reynolds number, Prandtl number, and we'll get our H value as 60.7 watt over meter square per Kelvin. In the second part, if the leading edge of the fin is rough, so that all of the boundary layer of film next to the fin is completely turbulent, calculate H. Okay, so when it says here that the leading edge of the fin is rough, so obviously the flow will now transition from laminar to turbulent. So we will be using this Nusselt correlation to find for H value. Okay, so this is the correlation, and then the Reynolds number, you calculate the Reynolds number, and then this one Reynolds number, and then Prandtl number from here, and then we know that Nusselt correlation is equal to HL over K, and then we can solve for H. So the H is 77.2 watt over meter square per Kelvin.